Alright, hi Jen. Now, I just went over all the other stuff. I don't know if you're watching this immediately afterwards, but either way, the comparison test is essentially what we have to do for if the limit does equal 0 when we do the divergence test. Because as we set up here, it may converge or diverge. So this is one of those another tests that we use to figure out whether it converges or diverges. So first, let's just go over the conditions that you need to be able to do the comparison test. And I think it's really helpful, at least for me, to try break that down into kind of steps that you do when you're approaching one of these questions. So first, you say an is a series with non-negative terms. So your first line of working, if you're going to do the comparison test, should essentially be showing that this is true. So you should be specifying that an is always greater than or equal to 0. So, n is way too big. You'd write this, obviously, instead of an, you would write whatever the function actually is. And then you say, so the comparison test can be used, or something along those lines. You can kind of just paraphrase that. But you do need to show that you've checked that the function is always going to be greater than or equal to 0. Now, you can kind of think of the next two things as being pretty intuitive. I think of it in terms of a roof and a ceiling. So you're saying if you have a specific series such that that series diverges, and you have another series that is always going to be greater than that series, or equal to that series, then the second one will always diverge. And so if you think of it as a floor, Bn is your floor, and Bn goes up to infinity like this, it diverges to infinity, then An is going to have to also diverge because it's always either on line with this on the floor or it's above the floor, So eventually it's going to have to be pushed up to infinity. And by a similar kind of thought process, if you have Cn converges, which means it doesn't go to infinity, it flattens out like this, and An is less than or equal to Cn for all n, then An also converges. Obviously, it would hit the ceiling and go through it if it didn't converge, which means it either has to follow along it perfectly, if it's exactly equivalent, or it has to go below, which means it'll also converge to something else. So I think those 2 points are pretty intuitive if you try to break it down like that, and feel free to ask any more questions if you don't understand what I'm trying to say there. And then finally, to apply the comparison test, we're comparing a given series to a harmonic p-series or a geometric series. So the harmonic p-series is what I went over earlier, here. And so if we can find something of this form, we already know that convergence of p is greater than 1, divergence of p is less than or equal to 1, and so we can just make that comparison and do that. So I'll go through an example and you can kind of see how this all plays out. So like I said, first step, if you're going to use the comparison test, you need to specify that the function's always greater than or equal to 0. So 5 over n, 2n squared plus n plus 2 greater than or equal to 0. Obviously when n equals 1, you get like 8 over 2, 3, 5, 8 over 5, and it just stays positive from there. You're never going below the x-axis, and so you can state this. You don't need to show this. You just show that you're checking for it. So the comparison test can be used. And now you essentially go into trying to find a comparison that's valid. So when n's large, so you're not taking a limit, but you're considering what happens when n gets really big. 3 plus 5 over n over 2n squared plus n plus 2 is roughly equivalent to, and obviously it's not exactly equal, but this term here, when n gets really big, is essentially going to 0, right? So your numerator, you just look at 3, that's the only thing that really stays there. And your denominator, this 2n squared term is really going to dominate, right? Because the n plus 2 in comparison isn't really going to matter. So you can say it's roughly equal to 3 over 2n squared. And actually, I'll start a new line here. And if you take the series for 3 over 2n squared, it is the same as taking the constant out, which was one of the rules up there. I'll actually scroll up and show you, just to make sure that you know it's all vigorous. Where was it? Yeah, you can take the constant out just like this, because as shown it doesn't actually affect it. Which diverges, right? Because this, I mean, sorry, not diverges, which converges. And the reason this converges is because this here is of the form of our harmonic p series. 1 over n to the p, where p is greater than 1. So therefore it converges. So we expect convergence. And you can break down, so you do your comparison here, and now you break down, shoot, I hope I got I did get the text in, okay. Now we're going to break down the original function. We're going to try find a way to bring it down with inequalities and show that it always stays below, it always stays below something that converges. So since we think it's going to converge, we try to think of it as this sort of roof example. If we can find a blue line to be our ceiling, that it always stays below, then we can say our pink line converges, right? So to find that blue line, we're going to use, sorry, I don't have much space here. We're going to use inequalities. So we start off with our original function, 5 over n, 2n squared plus n plus 2. And we can say that is less than or equal to if we make the denominator a smaller number. So since n plus 2 is always positive, if we take that out, it's going to be a smaller denominator, which means a bigger overall number. And that's going to be less than if we have this 5, because the smallest possible value of n is 1, right? So if the top stays as 5, that's always going to be bigger than if it's 5 over n. So we get 8 over, because that becomes 3 plus 5, we get 8 over 2n squared, which is 4 over n squared. And then you can go 4 n equals 1 over n squared converges, and then you can justify it saying harmonic p series, I'm not going to type it all, where p equals 2. And therefore our series, our overall series, blah 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 blah, n equals 1, 3 plus 5 over n over 2n squared plus n plus 2 converges. by comparison test. And that's just about it for the working for that question. I think my brother's calling, so I'm going to cut off the video and start a new one later. Okay, hello, I'm back. I've called my brother and had lunch and everything. I'm about to go to touch rugby. I'm just quickly going to record this last example. So we're just repeating the comparison test again for this new one. So an equals n squared plus 4 over n cubed plus 5. And we say that n squared plus 4 over n cubed plus 5 is greater than or equal to 0, so the comparison test can be used. Now, the important thing to remember is that we're talking about a series, so n is equal to or greater than 1. Which is why we can make this statement. Obviously, if you take like n equals negative 100 and sub it into this, you're going to get a negative value. So we're essentially saying the unwritten statement is that we're considering n is greater than or equals to 1 when we say this. Now, first you want to figure out what kind of direction you want to go in with your inequalities. So to do that, you just kind of go for large n and have a look. N squared plus 4 over n cubed plus 5. You can ignore the constant terms for large n, because when n's really big, plus 4 plus 5 isn't going to really make a difference. So this is roughly equal to n squared over n cubed, which is equivalent to 1 over n. And we know from the harmonic p-series above that the sum or the series 1 over n diverges, and therefore we expect divergence. Sorry, I'm just going to scribble the ending there because I'm running out of room. Alright, so we're expecting divergence, which means if we go to here, we want to find the floor function and show that our function is always bigger than it, right? Because we want to say if something smaller than our function diverges, our function must also diverge according to this rule here, right? So let's start off with our n squared plus 4 over n cubed plus 5. Now, since we want this to be greater than or equal to something, we can either decrease the size of our numerator, or we can increase the size of our denominator. So let's start off by decreasing the size of the numerator, because that's easy enough. You just get rid of the plus 4, n squared over n cubed plus 5. And now to increase the size of our denominator, we also want to be getting rid of as many like frivolous terms as possible, so that we end up with something really simple, such as 1 over n, or some version of it, like a constant times 1 over n. And the way that we can do that is by saying, I know that n cubed plus 5n cubed is going to be bigger than n cubed plus 5. And therefore, as a whole, if that's the denominator, then the whole thing is going to be smaller than this, right? Because if you have a bigger denominator, you have a smaller fraction if your numerator is staying the same, you know? And that is equivalent to n squared on 6n cubed, which is equal to 1 on 6n. And you can say that 6 diverges harmonic p-series where p equals to 1, and therefore writing this out wrong. Therefore, our series n squared plus 4 on n cubed plus 5 must diverge by the comparison test. And that's it. So to summarize, for comparison, you essentially go state what your actual function is, state that it's greater than or equal to 0, so comparison test can be used. You kind of think about just intuitively what it looks like for large n and whether you expect it to diverge or converge. If you expect it to converge, like in this one, you try to find a ceiling function, something that's always larger than it that you know converges, such as this. And then if you expect it to diverge, you do the opposite, you find a floor. So you try to go low and simplify to something you know diverges, and you say if r1's bigger than this and that diverges, then our function must diverge as well. Hopefully that makes a bit of sense. Feel free to ask me any questions if you're confused, and yeah, I'll go on to the ratio test maybe tonight. I'll see how you're feeling about needing more videos.